Alright, part two. So I kind of cheated there because I was in a hurry to get that tucked in. And if I really look at this closely, this red arrow is actually 5.5 centimeters. So by scale, I would have called that 11 meters per second, but I was kind of cheating because I knew what it should be numerically. So when I'm doing this right triangle decomposition thing, okay, it's a right triangle here because the vertical is going to be perpendicular to the horizontal. I can also just use SOHCAHTOA, so I could do sine 30 degrees equals opposite over hypotenuse. Okay, so that's going to be VOY over 20 meters per second. Solve that through 20 meters per second times sine 30. Sine 30 is a good one to know. That's half. So this is going to be 10 meters per second. And then for the horizontal direction, that's going to be cos 30 equals VOX over 20 meters per second. Work that through, and I'm going to get VOX to be close to 16. It was 17.3. And so then I'll use those for the rest of the problem. Those tell me the initial velocity on my Vx graph and the initial velocity on my Vy graph. Okay, so to make this a little more useful, I'm going to double those quantities. So we're launched at 30 degrees still, above the horizontal. You always want to look to see if it's above or below. So there's 40 meters per second, so now that makes VOY 20 meters per second, and VOX, the original horizontal velocity, 34.6 meters per second. So go in and draw my velocity versus time graphs for the x direction. That's pretty simple, Vx versus t, and this is going to be just like that, and it's going to stay constant at 34.6 meters per second. And whenever it is that this thing hits the area bounded by that rectangle, is going to tell us the delta x, the range, the change in the horizontal position. And then the Vy graph is going to be a little more exciting. I know that this thing starts with a y velocity of 20, and I know that the slope of this line is going to be downward and negative, and so then it just matters when or where does this thing hit. If I know that it ends up at the same level that it started at, YO equals YF, then that's gonna look like this, and the positive area and the negative area will balance each other out, so the delta y would be 0. If it lands at a height above where it was fired, then I'm going to be somewhere along here. Maybe I'm just here, and the change in the vertical position is just going to be this positive area plus this little negative area here. Or if it goes and lands somewhere below where it started, if the delta y is negative, then maybe it's like this, and I just find all this green area plus the blue area would end up being negative there, because it landed at a height lower than it started at. And again, provided that it makes it to the peak of its motion, if we go back and look at that image, provided that it makes it all the way up to this high point, then that's where the vertical velocity is 0. That kind of defines this area then. If we know that this is 20, that's the height, and we know that the slope of this is negative 10, we can figure out how high up it goes. We can figure out what is this time here. We might call that t high or whatever. T2 doesn't really matter. So we can go through and math that out. Alright, the acceleration equals change in velocity divided by time interval. So I know the acceleration is negative 10. change in velocity in this first part. We go from a vertical velocity of 20 to a vertical velocity of 0. So 0 minus 20 meters per second, and I want to know how much time that takes. So I'll use a little algebra here. Time equals 0 minus 20 divided by negative 10 meters per second. This is meters per second per second. So my answer in the end is going to be seconds after those cancel out. And yeah, that takes 2 seconds to get to this point. So then I know the base and I know the height. I can find the area equals 1/2 base times height. So 1/2 2 seconds times 20 meters per second. Half of 2 is 1. 1 times 20, we're going to have 20 meters. That's the maximum height it will rise to on its way through its trajectory. If I just draw that again, it's going to look something like this. So we just figured out that the delta y max, or whatever you want to call it, is 20 meters. Again, every projectile motion problem is 2 problems, so while it was doing this vertically, it was doing this in the horizontal direction. So during that 2 seconds, if I come over here and drop this down, let's say that's 2 seconds, then this area represents how far it moved downrange from where it was fired. So I can just take 2 times 34.6, and we're at 69.2 meters in the first 2 seconds. That's how far we would have gone. If it ends up landing at the same height, then I know that we're going to go over here, and by symmetry, I know that this is going to be at 4 seconds. And so again, here's 4 seconds. And so where does it land? Well, it's going to land twice as far away. So we just take that and double it, and we're at 138.4 would be the total. So 69.2 meters going up. Sorry, it's moving horizontally 69.2 meters during the upward portion, and it's also going to move a further 69.2 meters during the downward portion. So the total change in horizontal position there is going to be 138.4 meters. So that's, again, if the original and final vertical heights are the same. So the change in vertical is 0. This area plus this area adds up to 0. If that's not the case, because this was a cliff that it was thrown off of, so it's going to end up continuing this parabolic trajectory down that way, and YF is down here, and YO is way up here, then we're going to continue this triangle out, and perhaps I know the change in Y. I know that this is, say, the 30 meter level, and this is 0 meters. So if this isn't the case, if delta Y is, let's see, changed, so final minus original, if delta Y is negative 30 meters, then what does that mean here? Does that mean that this area is negative 30 meters? No, because the total area has to add up to that. So I know my positive area is 20. So what does this have to be in the end so that I get a total of negative 30? So we've got 20 meters plus equals negative 30. So I think about that, and okay, this is going to have to be negative 50 meters then, because we're going to have to, we're up here, this is 20 meters above our starting point, and this is not scaled. We're going to end up down here. This is 30 meters below our starting point, 50 meters below our maximum height. And so with this triangle, I know that the area is negative 50. but I don't know how much time this takes. I could maybe make some kind of a scaling argument. And I don't know what this final vertical velocity is. I just know how they relate to each other. That's by the slope. So again, if this is 1 over, then this is negative 10 down. If this is 2 over, this is negative 20 down. So I can call the base t, and the height will be negative 10t. And if I push that through, negative 50 equals negative 5 t squared, negative 50 over negative 5, negative over a negative, so this is 10 equals t squared, and so the time beyond the maximum height is root 10, okay? So square root of 10 represents how much farther we go here, so that time is going to be 2 plus root 10 seconds, okay? That would be the total time that it takes to get down here below, and that's basically most of what you would have to find in a projectile motion problem.